Welcome to the lesson on the activity series with regards to chemical reactions. Just an important note to remember, a chemical reaction is a process in which reactants are converted into products. What's important to remember is that for all chemical reactions and all processes, there's a conservation of energy and mass. So with regards to reactions, that means that the atoms that appear on the reactant side should appear on the product side. Okay? Just something that's always good to keep in mind. How do we predict reactivity? This is a complicated question, but the way that we can do it is we can use the activity series, which is table J of your reference tables. So the activity series is not comprehensive by all means, so as you can see, not all elements are on this table, but it does give us an idea of how, to predict if elements will react or not. As you can see, the table is arranged from most active to least active, and you have metals on the left and nonmetals on the right. It's also a qualitative chart, so there's no numbers here, there's no values. It's just a list, and the way that you do it is you basically rank the elements based on their position. Okay, so if an element is higher on the list, it's more active than something lower on the list. So for example, I could say that magnesium is more active than titanium and manganese, but I don't know how much more active. Okay. This list is useful for predicting single replacement or single displacement reactions, which is what we're going to be doing today. A quantitative list is actually used in electrochemistry, where we see the reduction potentials of different elements. So you will see this again when you study EChem and redox reactions. All right, so what does it mean to be active? High activity means basically high reactivity. So elements that are high on the list are going to be very reactive. Okay, for metals and nonmetals, this kind of means slightly different things. So for metals, high reactivity means that these atoms will form cations easily. So these elements will lose electrons very easily, okay? So metals toward the top of the list will easily lose their electrons, whereas metals towards the bottom of the list do not lose their electrons easily, okay? Cations from these elements tend to gain electrons to reform the neutral atom. And we see this a lot when we think about noble metals. So if you look at the bottom of this list, who do you have down here? You have silver and gold. These are noble metals. What do we use these for? Jewelry, right? Why do we use them for jewelry? Because they don't react when you wear them, right? You definitely don't want your jewelry reacting while you're wearing it. So we choose those metals based on their inactivity, right? Whereas if you look at the top of the list, those metals should look familiar to you. Look at those first four: lithium, rubidium, potassium, cesium. Those are your group 1 metals. You know that group 1, when we studied periodic trends, group 1 has very low ionization energies, very low electronegativities, meaning they will lose their electrons very easily. All right, so hopefully this is in agreement with everything that we've been saying thus far. For nonmetals, equal but opposite, as we usually see. So for nonmetals, being reactive means that these atoms will gain electrons very easily to form anions. And you should see a familiar face here, fluorine. Fluorine should always ring your bell because it's the most electronegative atom on the periodic table. It has an electronegativity of 4.0. We know that fluorine loves electrons, so it makes sense that it's the most reactive. All right, kind of similar, to what we saw with the metals. The most reactive nonmetal will be at the top. Fluorine, again, should be familiar to you. The least reactive is at the bottom. If you look at this, the nonmetal list here, you see a trend, right? These are all your halogens. As you go from the top to bottom, you should notice that you're going down the halogen list, right? So as you go down the list, electronegativity decreases, right? Atomic radius increases. So iodine is going to have a weaker pull on electrons than fluorine, so it will be less reactive. Cool. All right. What does this mean for a reaction? Elements that are more reactive would rather react, obviously. So that manifests itself in the fact that these atoms would rather be in compounds, okay? Elements that are less active would rather be in their elemental form. So we use this list and the relative positions of the elements to predict whether or not a reaction will proceed. Yes, okay. So we use it to predict reaction spontaneity. A spontaneous reaction is one that will proceed without intervention under a set of conditions. So whenever you define a reaction, you always define it under temperature and pressure. So let's look at example 1 here. We have magnesium and cobalt chloride reacting to form magnesium chloride and cobalt solid. So as you should have recognized, or as you should be able to recognize, this is a single replacement reaction. Magnesium is replacing cobalt. So as you can see, magnesium was an element and now it becomes a part of a compound. Vice versa for cobalt. It started as a compound and becomes an element. So the question is, will this reaction proceed? Is this true? What we have to do is we have to go over here and look at table J. I need to go and find these metals. So as we said with chemical reactions, right? Some things to always remember, when you have replacement reactions, metals can only replace metals, non-metals can only replace non-metals. So when you're looking for things on this list, you should only be comparing elements on the same side of the list. Okay, so you should only be, for this example, you're only comparing elements from the left side. You should never be comparing an element from the left and the right. Okay, if you did that, you messed up somewhere. Okay, so anyway, back to this. We're comparing magnesium and cobalt. Magnesium is here, cobalt is here. Magnesium is higher up than cobalt. So that means that magnesium is more reactive than cobalt. So magnesium would rather be in the compound, right? So if the reaction is proceeding and we're talking about spontaneous reactions, then the products should have the more preferential element in the compound, right? So the product should always have the more active element in the compound. And in this case, that is true. So we would say that this reaction does indeed proceed. So example 1, yes. Example 2, aluminum sulfate and nickel reacts to form nickel sulfate and aluminum. So we have aluminum and nickel replacing each other with the sulfate compound. So let's take a look over here. You have aluminum and nickel. So aluminum is more active than nickel, so aluminum would rather be in the compound. Okay, so if we come back to our reaction, aluminum is bonded to sulfate in the reactants. So nickel will not replace aluminum, so this reaction would not proceed because the reactants are actually the preferred state of both of these elements. Okay, and lastly, oh, we can't see this because my head is chopping. Okay, well, it's copper sulfate plus iron goes to copper plus iron sulfate. Let's just see this reaction happen. All right, so this reaction does indeed proceed according to table J, and this is a lovely reaction, so let's watch. All right. Single replacement reactions are usually very beautiful because you have a solid metal forming, right? So what's happening is you had copper sulfate solution and iron. So the iron is at the base of this, and as the reaction proceeds, you're forming copper metal on the surface, and iron is actually getting dissolved in the solution. So just very quickly, once again, you see this is clearly copper here, this bright red stuff. All right. Now, something else that you should notice is there's a color change going on. So copper sulfate is lovely because it's a really rich blue solution. It's kind of hard to tell on this video, but because it's a yellow background, but it makes the solution look green. And now the video starts with copper already deposited, but we know that iron is like a silvery gray color. So what happens is you see a color change. You see the copper, the reddish brown substance deposit on the surface. And then you actually see the solution color change. So that's what I want you to focus on when I play it this time. The solution starts off very blue, so it looks green in this image. As the reaction proceeds, you see that solution actually getting lighter in color, and eventually it's completely clear or yellow, kind of matching the background. So again, with reactions, you always see, or not always, but you can usually see them happening. You usually see a color change, or you see some bubbling, or you see, solid forming, something disappearing. So, these are lovely reactions to watch. Okay, so let's practice. Can manganese replace cesium in a substitution reaction? Why or why not? This is very straightforward, classic Regents question. So manganese is here, cesium is up here. Cesium is more active than manganese, so cesium would replace manganese. Manganese would not replace cesium. So the answer here is no, because cesium is more active than manganese. All right, which is the most reactive metal on this list? That would be the metal at the top, so that would be lithium. The least reactive metal would be gold. And again, this is why we wear gold. This is why gold is our jewelry of choice. All right, question 3. Which is the most reactive non-metal? Explain this in terms of electronegativity. So we went over that. Fluorine is the most non-reactive metal because it has the highest electronegativity, meaning that it attracts electrons the easiest, or the strongest. It has the strongest attraction for electrons. So it will preferentially form the negative anion. Okay. So finally, these are the most difficult types of questions that we could ask. So predict whether or not the reactions will proceed. If yes, predict the products of the reaction using the crisscross method. If no, write no reaction. Excuse me. So silver plus potassium nitrate. Okay. We'll just list all of these very quickly here. Okay, so silver plus potassium nitrate. Let's look. Silver is at the bottom, potassium is at the top. Potassium is more active than silver, so this will not proceed. So we're just going to write no reaction here. Okay. Zinc plus silver nitrate. So we have zinc is here, and silver is down here. So zinc is more active than silver, so zinc would preferentially be bonded to the nitrate. So when we're doing this, then we would pull silver. Silver would come out as a solid, and you would have zinc nitrate. Zinc as an ion is 2+, and nitrate as an ion is 1-, which you can get from the reference tables as well. So when you do this, NO3 minus 1, and you do that crisscross, remember that you bring the charges to be the subscript of the other ion. So this 2, you lose the charge, the 2 comes down to be outside the parentheses for NO3. And the 1 for the nitrate would go down to be next to zinc. So this would be Zn, NO3, 2. All right. Now, we haven't learned about balancing equations yet, so it's all right if you don't put the coefficients in yet, but to balance this equation, to make sure all the atoms are balanced, you would put 2 as coefficients here. All right. So let's look at the next one. All right, we have Cl2 plus Ki. So in this reaction, we're actually looking at the anions, the nonmetals. So I, Cl, and I. Chlorine is more active than iodine. So chlorine would rather be bonded to the potassium than iodine would. So this reaction will proceed. All right, so iodine is going to come out, and iodine exists as a diatomic element, so we always have to write it like that. And then the potassium is going to be bonded to the Cl. Again, you have to use the crisscross method. I know that potassium is a +1 element and chlorine is a -1 element, so that's how it's KCl. And again, if you're balancing the equation, you would put the coefficients of 2 in front. If you didn't get that part, that's okay. Alrighty, let's look at the next one. Li plus H2O. will this reaction proceed? So when you're looking at this, you're actually looking at lithium and hydrogen. Hydrogen in this case is going to act as the cation. And hydrogen is down here with the little stars next to it. Lithium is up at the top. So this reaction, lithium is the most active element. So this will definitely proceed. And what's going to happen is you're going to pull H2 out of solution. And you're actually going to, the anion of H2O is OH minus. So you're going to be forming LiOH here. And hydroxide has a charge of -1, lithium has a charge of +1, so it's a 1-to-1 ratio here. All right, and again, you would put 2's in front to balance this equation. If you don't get that though, that's okay for now. All right, let's look at the next one. Copper plus aluminum sulfate. So you have copper is at the bottom, aluminum is right here. So aluminum is more active than copper, so aluminum would rather be bonded than copper would. In the reactants, aluminum is already bonded, so copper is not going to replace aluminum here, so we would say no reaction for number 5. And 6, again, you're looking at anions here. So you've got bromine and iodine coming over to the chart. Bromine is more active than iodine, so bromine will replace iodine in this compound. So we would simply have calcium would now be bonded to the bromine, so it would be CaBr2. Iodine and bromine have the same charge, so I can actually just replace them in the formulas. And then I2 would come out of the compound. And finally, zinc and sulfuric acid. So we're looking at cations here, zinc and H2. Hydrogen is fairly inactive. Zinc is more active than hydrogen, so yes, this reaction will proceed. Again, kind of as we saw earlier, hydrogen is going to come out as H2, and you are going to form ZnSO4. Zinc always goes 2+, sulfate is 2-, so this is going to be a 1-to-1 ratio. All right, and that is it for this practice. So hopefully that was fairly straightforward, and we learned a little something here. So using table J, again, the being more active means that that element would rather be in a compound. So predicting reactivity is really just about, is the most active element in the compound yet? No? Okay, the reaction will proceed. If the most active element is already in the compound, the reaction will not proceed. All right, so if you have any questions, you can drop it in the comments or email me. Otherwise, have a good one.